Okej, mitt namn är Marcus Levin och för jag är inte dansk och för att säkerställa att så många som möjligt förstår vad jag säger och för att säkerställa att jag ser det jag vill säga så vill det här föregå på engelsk. Jag hoppas det är okej. And I'm going to talk a little bit about reliable measurements of exposure to airborne engineered nanomaterials. Anne mentioned it a little bit briefly earlier about the inhalation exposure, and all exposure that I will talk about will be aimed at measuring for the inhalation route and not for dermal or ingestion. The inhalation route is also the most important one for the toxic response, and the position of particles in the lung is generally divided into three sections of the lungs. We talk about the head airways, which is the upper part of the lungs. We have the trachobronchial region, and then finally the alveolar region. And these different regions are very important because the deposition in them is strongly dependent on the particle size, as we can see in this graph here. So it is always important to know the particle size if we want to connect the dose with the exposure, or the exposure with the dose. As Anna also mentioned, there are a lot of different metrics we can use to measure our exposure. We can measure number, we can measure mass of the particles or surface area of the particles. And it's still quite unclear which is the most important one. For some aspects and some endpoints, surface area seem to be quite important. And just to highlight this a little bit more, we can look at two fictive types of aerosols. That is a gathering of particles. If we have aerosol A with 20 nanometer particles and aerosol B with 200 nanometer particles, and 10,000 particles of aerosol A and 100 of B. If we just measure numbers, then of course we have a higher exposure with aerosol A. If we measure surface area, then we have the same exposure. If we measure the volume, which is linked to the mass of the particles, then we have a much higher exposure with aerosol B. And if we look at the long deposited surface area, where we take into account how much of the particles will deposit in the lungs, then we can see that again aerosol A seems to have a higher exposure. So regardless of what metric we measure, we always have to know something about the size if we want to link the exposure with the lung deposited dose. And if we want to measure size, we can do this in a lot of ways, because it will never be feasible to look at every little single particle that we inhale and determine the exact size of it. So instead of knowing the exact size, we have to study some parameter or observe some parameter of the particle, which we can then link with some type of size of the particles. For example, we can look at how the particles scatter light, or how it behaves due to gravity. Or, as I've been focusing in my work, how particles behave in electrical fields. And I don't want to go into details with the theoretical parts of this, but I just have to mention a few things to understand the problematics that we experience. When we want to look at how a particle behaves in an electrical field, we look at the electrical mobility of the particle. And that is basically just if we take a charged particle, put it in an electrical field, it will of course move. And the relationship between the velocity of the particle and the strength of the electrical field is the electrical mobility of the particle. And based on this mobility, we can link it to a particle size. This is a very commonly used technique. We use it in the scanning mobility particle sizer. There's a spelling mistake there. The fast mobility particle sizer and the nanoscan and so forth. A lot of instruments use this. And to be able to use this, we have to precondition the particles a little bit. So we charge them. And this is normally done by introducing them to a lot of ions, which will randomly stick to them, and some sort of equilibrium will be achieved. This can be done unipolarly, when we have just one polarity of ions, or bipolar, where we have both polarities of ions. I have mainly been working with unipolar charging, and now there's some equations here, but the important thing here is that if we do this, then we should be able to link the number of ions with the particle size, so that if we then measure this, we can always link it to a particle size. And this is a fundamental thing in measurements, that we condition it somehow, and then we should be able to link that with the particle size. And this can also be nicely used in another instrument that doesn't measure size, but directly measure the long deposited surface area, which Ann talked about earlier. And this is quite nicely done if we can get an instrument which simply is an electrometer, and we can precondition the particles so that they have a number of electrons to particle size relationship of 1, or the p to the power of 1 rather, because if we multiply the surface area is the particle size to the power of 2, and the position fractions in some specific regions can be approximated as particle size to the power of -1. So if we multiply them to get long deposited surface area, it is the same as a response from a pure electrometer with the correct preconditioning. And this instrument is used a lot in measurement of exposure, and I will show some results from it later on. That's why I wanted to explain a little bit how it works. Then we again come to the problems of non-spherical particles. Anna also mentioned that the toxic response can change a lot with different shapes, but so can also the measurement of particle. It can change a lot with different particle shapes. Because how do we define the particle size of different shapes of particles? For a sphere it's easy, we have the diameter. For an agglomerate, we can usually define some sort of diameter. But then as we move into more and more complex bundles of fibers, it becomes quite hard to visualize what the diameter of them actually is. And these non-spherical particles also affect a lot of things, such as the charging of the particles. We have this nice relationship, as I said, when we precondition them, but if they're not spherical, then this relationship will strongly change, so we will not get the response that we wanted to get. And then there's also a lot of effect on drag and so forth on the particles. And this is a very important problem, because if we measure particles in the workplaces, we quite seldom see these perfect spherical particles. For example, powder handling, we always have agglomerates and aggregated particles. So it is quite important to remember that what we measure, the response of the instruments can be quite dependent on what we actually measure. So to be correct, we have to know what we're going to measure before we measure it, and then it becomes a circle of not really knowing what we're doing. To investigate these things a little bit, I made some studies in the Nanosafety Center where I compared some different commonly used instruments. I compared them for measurement of particle size, particle numbers, and this long deposited surface area. And we did this using some typical powder nanomaterials, which can be used in industry. And we aerosolized them using a dustiness drum. I think Kjeld will mention the dustiness drum a little bit more later. No? Oh, I thought I saw it on a slide. Okay, then he will not do that. And then also on some spherical particles, just to make sure that we know what we're doing. And if we look at some of the results of the measurement of long deposited surface area, these here are comparison between some of the commonly used instruments. We have FMPS and LP on the x-axis here, and NSUM, which is this directly measuring long deposited surface area instrument that I described. And we look at the spherical particles. So this here is the 1-1 line. We can see that for spherical particles, we have a great comparability, as it should be. This is what they are calibrated for. But if we then look at the more realistic powders, we can see that suddenly there is quite a big dependency of the particle type and the material type. And this here is a logarithmic scale, so the difference in measurement between the different instruments is actually quite big. For some types of materials, we can be 10 times higher for some instrument than the other. So it's a little bit hard to directly compare these instruments. And this is why it's important to remember that our exposure measurement might actually be dependent on what instrument we go out and measure with. And if we look at this closer to figure out why we have such a big disagreement, we can see that again, two instruments measuring on the same type of particles give totally different size distributions. Here we have in blue FMPS, which claims that we have a lot of particles around 150 to 200 nanometers, while another instrument claims that we have a broad size distribution with particles around 1 micrometer. And of course, if we take into account that we have different deposition fractions for different sizes, the exposure assessment based on these results would be totally different. So again, the choice of instrument affects the exposure assessment. Now, of course, when they are this different, one of them has to be incorrect and one has to be correct, hopefully. And if we study them a little bit further, just to highlight that one type of problem we can have with our instruments can be a fundamental problem. In this graph, we see the mean diameter measured by some different instruments. We have SMPS, which is generally a good reference to have, and FMPS and LP. And the last graph, we saw FMPS and we saw LP. And we can see that in red here, the LP agrees very well with the SMPS. The FMPS agrees very nice for small particles, but not nice for bigger particles. And in my studies, we went further with this and found out that this was a fundamental problem of the instrument. So we found out that this instrument, which has been used quite a bit in exposure assessment, could not be used for this. So it is important to, as a start point, figure out which instrument can actually measure these complex particles that we use, because a lot of instruments which are used are not built for this. So there is some fundamental problem in going out and measuring particles and determining the exposure. Another problem, which is not such a fundamental problem or not as strong problem as the FMPS problem, is that even though they might be measuring correctly for some particles, again, we have the dependency of particle shape. So these areas for some small hand-carried instruments, which become more and more popular because they're cheap, they're easy to use, and you can have them continuously running in an industry. And we can see for some particle types, we have two different small instruments here, and they're compared to the FMPS for lung deposited surface area. For some particle shapes, we have a fairly good agreement, actually. For some other, we have a really poor agreement. And again, for some other, we have an okay agreement. So once again, we can see that if we want to measure something, we actually have to know what we're going to measure before we measure it, in able to measure it correctly. So it is a little bit of a tricky situation where it becomes hard to go out and just measure something and determine that this is the exposure here. It needs a lot of work to be able to build up a knowledge about what kind of particles we are measuring, how we should measure, which results should we trust, and which results should we discard. And just to conclude something about this, we can see that we have some problems with the current instrumentation. We have some specific instrument problems, where we can see that some instruments are not meant to be used for this. And then we have some other instruments which are good to use for this in some cases. But we have a problem with non-sphericity, where we basically have to calibrate the instruments for the exact type of particles we want to measure. And in a lot of cases, we measure a lot of different particles at the same time, so it's not possible. If we want to somehow move forward with this and be able to do good measurements, we have to develop both strategies and techniques for measuring different type of metrics for particles, and especially if we want to base occupational exposure limits on the lung deposited surface area, which seems to be a key metric, then we have to have a better strategy to measure this, because as it is now, we cannot do it reliably. There are some different ways of achieving this. Either way, we can take the simple approach and just harmonize everything so everybody measure with the same instrument, and then we have a relative measurement where we can say that, okay, we think it's a bit higher here than in this place, but this is a dangerous route to go because, as I said, different shapes of particles react differently, and as we move into complex shapes, it might not give a good relationship between exposure and outcome. And then the good approach would be to develop some new techniques, but it's hard to develop new techniques, and any new techniques would most likely be costly and bulky, and that goes totally against the current demand of instruments, where it is in high demand to have something small and simple, but then we have to cut back on the accuracy. So it is a difficult balance to achieve. And with that, I conclude my presentation, and will give the word to Kjeld for the next presentation. Thank you.